All right, continuing our induction argument. We had case 1, which was where all of the sets we were using were strictly smaller than. So for every possible set we could pick, they were smaller than. Well, what's the opposite of that? Not all, but at least one is bigger, right? But it can't be truly bigger because we're taking a subset of X, so it's got to be equal to. So there exists some subset where the neighborhood is exactly the same size wait a second. If I have a graph and then I take this one subset and the neighborhood of X is exactly the same size as X, since this is a simple graph, there are no loops. And that means that all of the elements in X can be made into a bipartite graph. Because remember, the neighborhood was in the other partite set. We're starting with a bipartite graph. So let's let F with these partite sets. Wait a minute. What do I know about that graph? What do I know about this new graph F? That is important in terms of the way I am doing this proof. What kind of proof am I doing again? Induction proof. I have a smaller bipartite graph. It's X is a subset, but not equal to U. If it's smaller, my induction hypothesis comes in. What does it mean for Hall's condition to be satisfied on this new graph?
vertices in the neighborhood.
Then, that's an if. What's the then? You wrote down Hall's condition repeatedly on Friday. It's not up here. Show me in your notes what Hall's condition is.
Number of vertices in the neighborhood of x is greater than.
That's the if. What's the then? If the number of vertices is smaller than the neighborhood, then what? Aha! So that means that G contains, in our case, F contains a matching for this set X. Now what's a matching again? It's a one-to-one and onto function. Why is it onto? Because the neighborhood is the same size as X. So if it's a one-to-one function and the two have the same cardinality, it has to be one-to-one and onto. Now, normally I would say with a subset of, but I can't have a one-to-one matching. If the two sets are the same size, that's not onto. Okay, wait a second. That's in U, NX is in W. I've matched X perfectly with NX. What about the rest of U and the rest of W? Well, again, that would be a bipartite graph. And instead of having U and W, it's got U minus X and W minus NX. What do I know about those sets? I don't know that because U is necessarily less than or equal to the cardinality of W. So W minus NX could be bigger than U minus X. X and NX were definitely the same size, though. U and W might not have been.
Matching between those sets.
Why?
Because if U is less than W, then W minus NX would still have more vertices than U minus X.
And one more critical statement.
So the neighborhood of X would have more vertices in it.
But I'm not looking at the neighborhood of X anymore. I'm looking at the neighborhood of U minus X, right?
Well, then the neighborhood of U minus X would
I don't know that to be true yet. That's the problem. I would love to say that all of these vertices only go to vertices in here. But some of those vertices may be connected to vertices in NX, couldn't they? Crap. Ooh, so close. I was so close. If there was a guaranteed split and none of the vertices in X went anywhere other than NX with all of their edges, I'd be okay. We only know they go no other places than NX in the matching. They might still go other places outside the matching. Crap. All right. So let's take a subset. Let S be any subset of U minus X. Consider S prime to be the neighborhood of S, but only the part that's in W minus NX. So there, Reese, that's how I'll make the restriction lower. I'll say, oh, let's take a look at this. And now I need to answer the question, is the size of this set bigger than the size of this one? Because if it is, then you're absolutely right. Hall's criteria applies. There's a matching between these parts. And then I've matched inside X, and I've matched outside X, and I'm good to go. But I need to show this. Now remember, we were saying that the neighborhoods were at the very worst equal to. So let's not just look at S, let's look at all of U. The neighborhood of U is bigger than or equal to the size of U. But instead of writing it as U, I'll write it as X union S. Okay, unions and intersections. The neighborhood of X is NX, right? S prime never touches NX, does it? So the part that touches X is completely contained in the neighborhood of X. As a matter of fact, wait, let me erase that. That's not a less than or equal to. That's an equal to. That's equal to this, right? That's bigger than or equal to this. That is bigger than or equal to X union S. Wait a minute. What do you know about X and S? That thing right there. What do you know about S and X? S is a subset of U minus X. There might be other stuff. But it guarantees me that S and X are disjoint. If you're counting the union of two sets that you know are disjoint, you count all the things in one set, you count all the things in the other set, and then you take away the stuff you double counted. How much stuff did you double count? Nothing. Oh, wait a second. Look at the outside edges. So, the size of NX plus the size of S prime is bigger than or equal to the size of X plus the size of S. What do you know about the size of NX and the size of X? Those are the same. Therefore, size of S prime is bigger than or equal to the size of S, which is exactly what I claimed, isn't it? If that's my claim, then, Reese, what can I say about those sets? Which means there's a matching from here to here, because there's a matching into a subset of here, which means I got the matching I wanted. I got the matching between X and the neighborhood of X, and I got the matching between the rest of U and some subset of W that avoided the neighborhood of X. Hey, wait a minute. I now have two matchings. The matching from X to NX and the matching from U minus X to the rest of W. Glue these together and you have a matching from U to W. And that finishes our proof. Not short. Now, the reason that I did this all in sets is because that's the way Hall did it himself. He didn't actually do this as a graph problem. He did this as a set problem. Why? What does this mean in sets? Here is a question that sounds completely unrelated. How many of you have been on student government? How many things did you represent on student government? As a matter of fact, in the student government bylaws, it says rather explicitly that you can represent up to 2 different student groups at a time. What if I refuse to allow you to represent more than one? Each group needs its own distinct representative. Can you do it? You cannot choose the same person twice. So there are no repeats allowed in that set of X's. Here are 7 student groups. Can you find a set of distinct representatives? What I would do is I would consider the neighborhoods of each set. So set 1 is 1, 2, 3, set 2, 6, 4, and 2. Take the union of those two. That's the neighborhood of set 1 and set 2. Is it more than 2? Take any collection of sets here. As many as you want or as few as you want. Is the neighborhood, the number of elements you have, bigger than or equal to the number of sets you chose? Is the neighborhood of X bigger than or equal to X? If the answer is yes, then you can create a perfect match. In this case, I guarantee you I can do it. Set 1 contains 1, set 2 contains 2, set 3 contains 3, 4 contains 4, 5 contains 5, 6 contains 6, 7 contains 7. There's a unique representative for each group. I rigged this one. What about this one? Well, now there are fewer groups. Why not, Ben?
T6. I don't know, I was going through them, and T6 was the.
Well, you're right that 6 isn't in T6, but that's not
No,
just
I
it.
know, because there's 3 and 5 in T2.
As a matter of fact,
There's the 3 people for 2 things.
not just 3 people for 2 things, there's 3 people for 4 things. Look at T2 or T3 or T4 or T6. How many people is that? 3, 4, 5. The neighborhood of X contains 3 things, but X contains 4. The same proof in non-graph theory terms. This is Hall's original statement. But the union of K sets, that's K being our neighborhood. If I'm using 5 sets, I want at least 5 different options to pick from, or the neighborhood won't be at least the size of the original collection. Now, I don't know whose wise-ass idea it was to change the phrasing of this problem or to change the setup slightly. Let's make this Victorian, the marriage theorem. In a collection of R women and R men, a total of R marriages are possible between acquainted couples if and only if every subset of K women knows at least K different men. If the neighborhood, number of men known to any collection of women, is at least that big. Otherwise, people are fighting over the right partner, right? It doesn't say whether these are good marriages or not. It just says that they're possible. This is the same theorem, just phrased differently again. Questions? My goal is to find as big a matching as I can find. If I have an arbitrary graph, let's step away from bipartite. Suppose I have a graph of order n. What is the biggest possible matching I can have in this graph? At most, right? And since n could be even or odd, I'm going to have to round down. So it's less than or equal to n over 2 floor. If n is even, 2k, then it'll be k edges. If n is odd, 2k plus 1, it'll be k edges. If I have an even number of vertices and I have a maximum matching that is as big as it can get, then I have what's called a perfect matching. So a perfect matching matches every vertex in G. The proof of this follows directly from the proof we just did. It's a direct corollary. If it's one regular, then every vertex has degree 1, right? That means that it's copies of P1. Isn't that already a matching? Yay, that was easy. If it's anything bigger, then every vertex in X is adjacent to R things. But every vertex in NX is incident to at most R edges. And that means that the NX must be bigger than or equal to the size of X. I can't go more places than R times K, but then I have to divide by R again, so I can't go more than K places from K things. It's at worst the same size. If every woman knows the same number of men, we can pair them up. That's why the dating apps work. Okay. Well, with that in mind, let me think about independent sets of edges. That's what our matchings were, right? Independent sets of edges. Edges that had no common vertices on either ends. If my graph contains a maximum matching, then alpha prime is the size of that maximum matching. Which means a graph has a perfect matching if and only if its cardinality, its size is even, and its edge independence number is exactly half of its order. For a cycle, you'll only have a perfect matching if you have an even number of vertices, and then you take every other edge going around, right? If you have an odd number of vertices, then there's a vertex you can't hit because you'll be adjacent to one of the two on either side. What's KRS when I write it that way with the subscripts? Where one set has size R and the other set has size S. If they're not the same, I'm not going to get a perfect match because I'll be missing some vertices, and you can only match whichever one is smaller. And that's why I said R less than or equal to S here. So let's suppose I have a vertex and some edge that is incident to that vertex. So I have V, and then I have this edge E. Well, in that case, I will say that the edge covers the vertex, and the vertex covers the edge. If I have a graph with no isolated vertices, that's not the same as being connected. It's saying that your connected components all must have at least one edge. An edge cover, what do you think that means? An edge cover of G is.
Cover all vertices in G.
Exactly. It's a set of edges that cover every vertex. Now, clearly, the entire edge set covers all the vertices. But that's, of course it does. So the question is not how big can we make this, but how small can I make this? The edge covering number is the minimum cardinality of an edge cover. In other words, it's the fewest edges you need to hit every edge, every vertex. As long as we have no isolated vertices, this must exist. There must be a smallest possible cover. As long as my graph has no isolated vertices, there must be such a number and the edge cover that goes with it. Why do I know a minimum edge cover must exist? And I said if G has no isolated vertices, then I've got to be able to hit it with at least one edge, right? So I can start like we did with spanning trees, and I can start throwing edges on there until I hit everything. But it doesn't actually have to be a tree this time. I only have to hit each vertex once. Think about a cycle. C4. C4 is a square, right? How many edges do you need to make a minimum edge cover? Why? Or the left 2 and the right 2, yes? Hexagon, I need 3. Pentagon, or a triangle. How many edges do I need to cover the vertices of a triangle? It's still 2. I need to hit one of them twice, but I have to hit these 2, right? And if I just hit those 2, I'm missing one. I got to get there somehow. So take n over 2, but this time around up. The triangle gave me 2. The square gave me 2. 1 over 1.5 rounded up is 2. I go up because I got to get to that other lone missing, otherwise isolated vertex. Ooh. So let's suppose I have a bipartite graph. One partite set size R, one partite set size S. How many edges do I need to make a minimum edge cover? You need to hit every vertex, right? How many edges? Draw some examples. 2 lines of dots and play connect the dots. You only go from top to bottom. It is S. The order to hit each of the S-size vertices. You have to start from R and go up or down, whichever way you drew the bigger side. But you have to hit them, and you can't connect any of the S vertices to each other. You have to go across to the R side. That may mean that the smaller side has some things that go to more than one place, but you have to hit each of those S. You need exactly S edges.
Hey, wait a second.
What were the alpha numbers? Alpha prime of G and alpha prime of Kn and Cn and KRS? Wait a minute, they were R and then the floor, weren't they? Edge independence. The biggest set of edges you can make with no ends in common. That's alpha prime. Beta prime, edge covering. You've got to hit everything. Adds up to the total number of vertices in your graph. Every time. That is not at all obvious, is it? Which really means I should prove it. I have 2 minutes. I'm not going to. Read the proof. But the downside of doing the entire Hall's theorem proof is that I need another half day to finish this. So we have more time for section 8.2 as well. I'm going to move our homework assignment since I haven't finished 8.1 yet. It would have been due Friday. Since I'm going to finish 8.1 on Wednesday, it'll be due Monday. You'll get an update to the homework list as soon as I open my computer up and change that. So if you came in late, come give me your homework, come pick up your other stuff, and I will see you all on Wednesday.